Hello. Uh, am I audible? Okay. Thank you. So, good evening, everyone. So, it's more than 7:05, and we are now starting. So, let's begin today's session. So, I'll be sharing my screen. So I hope you guys are able to see my screen and slides in presentation mode, in full screen mode. So, okay. So, I think we are now good to start. Good evening, everyone. Welcome you all to the week 4 of the doubt and problem solving session of the NPTEL course of Techniques of Material Characterization. And this week, so in the last week, we have started in the last week, something we have started like some interaction volume of this scanning electron microscopy, and we have also seen from our week one that the evolution in the microscopy, like firstly from the optical microscopy to the electron microscopy. So we are going in that direction, and this week also the mainly consideration is the electron microscopy. So as I have mentioned in the last lecture that in the electron microscopy there are several kinds of microscopy. So in week 4 you have basically cover a several topics which is related to the electron microscopy, and we are further moving towards the transmission electron microscopy. So in this week that we have got mainly some introductory or some theories about the transmission electron microscopy if you have seen the lectures. Okay, so we will be begin with our questions. So let's start. So this is probably from the interaction volume. This question is also because this week also the first lecture which has covered some Monte Carlo simulations and all of the when the electron interacts with the specimen. So the question asked the size of the interaction volume and the penetration depth of the electron. So they are asking the relationship between the electron energy, which is nothing but the voltage, and the atomic number of the material. So they have given some combination like, so they have given some combination of the voltage as well as the atomic number of the material. So I just want can you guess or can you tell, like as we have also discussed it in the last class, that what could be the phenomena that can be that can assure this statement, like the size of the interaction volume and the penetration depth of electrons. Okay, increase with increasing the electron energy. It is saying that when we will increase the energy of the electron, or you can say when we increase the voltage, and decrease with the atomic number of the material. Okay, so what could be the combination? Can you read the screen and can you say me the answer? Any one of you? Answer A. So, and anybody else wanted to guess? B or C? C option. Okay, okay. Okay, okay, fine. Anybody else? Okay, so so please guys be on time and join on time. Okay, so we will discuss. So one somebody has guessed the answer A and somebody has guessed the answer C. Okay, so this is the basically asking about when the size of the interaction volume, or you can say the penetration depth. Okay, so this is the this in the lecture we have seen there is a Monte Carlo simulation. From there we can derive the depth, what could be the penetration depth and the volume. Okay, so here like from the Monte Carlo simulation, it is saying that the probability of the scattering is taken into account by programs as well as important parameters. Okay, so what could be the parameters like voltage, atomic number, thickness, and the density of the material. Okay, so when any electron will interact with any specimen, so firstly for an example you have taken example of a human being. If human being is running and if it is interacting with some other human being, or you can say some specimen or the wall, you can say, then the energy of the human being is also important, right? So similarly when the electron is coming or interacting with the specimen, then the energy, okay, so energy is what here we are giving in terms of the voltage. So voltage is very important. Second thing, when you will suppose again I will give the example of the human being. When the human being will interact with any wall, so suppose if the wall is very thin, or suppose if there is some very thin something which is very thin, or you can say very light, then and something which is very thick or which is very heavy in weight, then that is so similarly the atomic number. Okay, when the electron is interacting with some lower atomic number or the higher atomic number, and what could be the thickness similarly, and the density of the material. So these are some parameters which is very important when any electrons will interact with any specimen. Okay, so we will see further. So as you have seen, so this is very simple slide. So there is two scientists, Kanaya and Okayama. They discovered the in 1972. These are the Japanese scientists, and they developed a range equation that considered both inelastic and the elastic scattering to give an estimate of the interaction volume. Okay, so they have given some range of the interaction volume. Okay, so for an example, as you can see in the below table, so here suppose if I will keep constant any atomic number. For an example, atomic I will be taking aluminum. Okay, and if I will be increasing the voltage, okay, so suppose 5 kilovolt, 10 kilovolt, sorry, 10 kilo electron volt, 20 kilo electron kV, and the 5 kilo electron volt. So when I am increasing, this would be I think 50. So here you can see the interaction volume, the size of the interaction volume is also increasing. So we can say when by keeping the constant of the atomic number, when we will increase the voltage, the interaction, the size of the interaction volume is also increasing from the nanometer to the micrometer. Okay, again the second thing is if I will keep the if I will keep any voltage constant. Okay, if I will keep the voltage or the energy constants, for an example the 5 kilovolt, 5 kilo electron volt, if I will keep, then if I will increase the atomic number, okay, then here you can see the size of the interaction volume is decreasing from the 450 nanometer to 413 nanometer to 159 to 85. Okay, so from here you can get the relationship. Here this plot is also saying the same thing which I have explained through the table. So here the answer would be increase with increasing the electron energy and decrease with the atomic number of the material. So this would be the answer A. So here increase with the increasing electron energy voltage and the decrease with the atomic number of the material. Okay, so here you can see this is relation also. This is uh, uh, RQ is the range defined as the radius of a hemisphere. Since this interaction volume is in the shape of the hemisphere, so this is giving you the radius, and also this is giving by the relationship. And here this A is the atomic weight, Z is the atomic number, and your E naught is the incident beam energy. So from this relation also you can say the R, which is the range of the radius of the hemisphere, or you can say the interaction volume, which is directly proportional to the energy and inversely proportional to the atomic number. Okay, so when we will increase the voltage, the R will also increase. When we will increase the atomic number, the R will decrease. Okay, so this will be the relation. I hope you guys understand this and it is clear to you. Is there any doubt which I have explained right now? Anybody else? Anybody is having any doubt or something? Is it clear? Oh, thank you. Okay, so here, as I said, that here we are moving towards the TM. TM is nothing but the transmission electron microscopy. So here, in every kind of a microscopy, the important thing is contrast, as we have seen from our previous lectures from the optical microscopy. So here it is asking that the contrast generation in TM images can happen due to the effect of mass contrast only, thickness contrast only, amplitude phase contrast only, all of the above. So if you have gone through the lectures and if you have understood this clearly, that how the contrast is generating and the evolving by differentiating or by varying the mass and the thickness and the amplitude, then how it is giving the response in terms of the imaging. So can you guys give me the answer of this question? Answer D. Okay, fine. So okay, let's see. I think answer D is correct. So here in this slide, you can see the contrast generation in electron microscopy is like that. So here you can see some particle and this could be the substrate. So here it is, I think, a micrograph of the gold and the titanium oxide catalyst. So here I will show you some example that how the contrast is generating or varying by the several parameters. So here it is saying that due to the scattering of the incident beam by the sample, the amplitude and the phase of the electron wave change, which result in amplitude contrast and the phase contrast correspondingly. Okay, so it is clearing that by varying the amplitude and the phase of the electron and the phase of the electron wave change, so that will also give you the contrast. Similarly, when we will see Similarly, when we vary the mass, so suppose if you will take the lower mass of any specimen and this is the higher mass, okay? So when the incident electron beam will come, okay? So since this is a lower mass, okay? So the scattering will be the less. So here you can see the mostly the scattering will be the less. But when the incident electron beam will interact with your higher mass of object or the specimen, then the scattering will be the higher. So suppose the intensity is here is the 100% you are giving as an incident electron beam, but here suppose for the lower mass 10% is lost, so you will get the 90%. Here due to the higher mass, here the loss could be the 20 or the 30%, then you will get the intensity of your 80%. Then this will be intensity profile will be like this. Okay, so here by varying the mass you can generate the contrast. So heavier elements represent more powerful scattering centers than the light element. Okay, so due to this increase of the Coulomb force with increasing atomic number, the contrast of areas in which heavy atoms are localized will appear darker than of such lighter atoms. Okay, so when we it is saying that the contrast area in which heavy atoms are localized will appear darker, okay, due to the difference in the scattering of the incident electron beam. So that's why here we will generate the contrast. Second thing is also the similar kind of a thing of the thickness contrast. It is also somewhere related to your difference in the scattering of the incident electron beam by varying the thickness of the specimen. So here you will also get a two different kind of a contrast by varying the mass. Okay, so answer will be the all of the above. So by changing the mass, by changing the thickness, by changing the amplitude phase, you will get the contrast difference in your TEM. Okay, so the next is what will be the contrast generation due to atomic number effect? This is again the same question in TM, and but it is giving you some example. It is giving you some example of the elements like in the bright field image of an alloy containing. Okay, so suppose it is a aluminium copper alloy. So if you will generate a contrast due to the atomic number effect. Okay, so as I have discussed in our previous slide, there is a mass contrast generation, thickness contrast. So similarly there is one type of contrast which is atomic number contrast. Okay, so due to the change in the atomic number, there will be the difference in the contrast of the imaging in the TEM bright field. Okay, so can you tell me the answer that what could be the relation or in this as per the atomic number effect? Why? Hmm. 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 Okay. Hmm. Huh. Okay. 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 Fine. Yeah. So he's right. So here, as you can see, this is also a one kind of a atomic number contrast. In this slide, it is showing. So here, this is giving the relation of the of some formula. So here, but he's right. So when we will, okay. So actually, but I think here the particle with a here it is showing, suppose this is a uh, okay, yeah. So here the when we will increase or the size of the several 10 nanometer appear with black contrast, since AU is by far the heaviest element in the system and therefore scatter many electrons. Okay, so since the AU is the heavier atom, okay, and here if you will see the here the copper will be the heavier than the aluminum because the atomic number of the copper is higher. Okay, so when the atom which is heavier, okay, will give you the more scattering, as here it is also saying that the gold here AU is the gold which is the heaviest element in the system, and that therefore scatters many electrons. Okay, so here that's why it is appearing darker. Okay, so here you can see in this image AU particles black patches on TiO2 support or the substrate. So since here the element which is heavier or which is having a higher atomic number, which will show the dark. Okay, so here aluminum is the lighter as compared to the copper, so the copper will be the darker, so here the aluminum will be the brighter. Okay, so the answer is here that you have to understand by this example, since the aluminum is the lighter element as compared to the copper, so the copper will appear as a darker when the contrast will generate because it is having a high atomic number. Due to the less atomic number or the lower atomic number of the aluminum, which will appear as a brighter as compared to the copper. So here the answer will be aluminum will appear brighter as compared to the copper. Okay, so somewhere it is also, these are somewhere correlated to your mass thickness or your diffraction contrast, or you can say your atomic number contrast. So you have to see that how, so this is very important. So as you are just seeing it as a contrast generation, but it is not. So if we will see any kind of, because the ultimate our objective or goal is to get a good image even from the optical or from the SEM or from the TM. So if you will have some kind of a this kind of this knowledge which is a theoretical knowledge, that why it is giving this kind of a contrast, what could be the possibility or what could be the reason if you are using some copper aluminum alloy or any gold silver alloy, then if something is because that is alloy, why it is giving a different contrast, so then you would be able to answer this kind of a question. Okay, this could be the reason, and because of this, this is giving us such kind of a contrast. Okay, so just think in the direction of the practicality. Don't just solve it as a question, because when you will just solve this as a question, you will forget. By moving the lectures, you will forget. So you will just correlate with your day-to-day life or whatever experiments you are doing in your lab or in your colleges. I hope that you have some facilities regarding that. So this would be benefit, and you will have this for the longer of your I mean your research line. So the next question is in taking the selected area diffraction pattern. So this is just related to the instrumentation question. Okay. So where is the SAD? Okay. Selected area departure is placed. Okay. So before the sample, back focal plane of the objective lens, after the viewing screen, and there is no specific place. It means it is saying that we can place it anywhere. So, have you seen any some schematic of the TM? Then only you will be able to answer this. So, can anyone guess, and why you guys are not participating, or you are just seeing the whatever I'm saying? I hope you have gone through the lectures. Even if you not, then also you can guess on the basis of your knowledge. Okay. Is anybody else wanted to guess or to give some opinion or the answer? Please, guys, speak. This is just kind of an interaction session. Okay, here you are also seeing the lectures in your NPTL. Here also, if you will see some questions, then it won't be, because discussion will always be a good. That will also enhance your knowledge as well as mine also. So nobody wanted to guess or answer. Okay, fine. I can't do anything. Okay, yeah. So here, when you will see, okay, I will give you some better image which I have. So this is a more good image. So like in the electron microscopy or in the optical microscopy, you have seen that how these lenses are. So basically, this microscopy is nothing but the arrangement of your lenses and the apertures and your object and the source and your detectors. So how you are basically arranging this all together so that you are able to get a good image. So on the basis of this, the different microscopy has evolved. So here, if you will see that in TM, the electron source will come here. This is the anode. So the here the this will work as a cathode, and this will be the as anode. So here the condenser lens and the condenser aperture will be there, which will give you some focus of this incoming electrons, and here in between there will be the sample. So since this is a transmission electron microscopy, the coming electron will not just interact or scattered or diffracted from here. It will transmit through the sample or through the specimen. So here there will be the condenser lens. Similarly, on the other side, there will be the objective lens and the objective aperture. But here there is a one configuration which you will probably see in your further weeks lecture, which is called the selected area aperture. So this is here somewhere it is placed. Okay, so and there will be the projector lens, and there will be some more instrument which you will be see in further in the further next lectures, that what are the individual principle and why they are placed, and what is the individual the working mechanism and why it is advantageous by placing this. Okay, so here it is just asking about the SAD. So we have to give them the answer. So before the sample and back focal plane of the objective lens and the viewing screen. So before, okay, so this is the sample. So we can't see before the sample, it is only there is some you can say the STM scan coil, condenser aperture, anode, condenser lens. So it is not here, okay. And after the viewing screen, so you can see the viewing screen is here, okay, before this CCD camera or the photographic plate. So viewing screen is somewhere here placed, so it is not even after the here. So this is on the back focal, since the objective lens is here and somewhere here will be the focal plane, because lens is here and the back focal plane of this objective lens will be here. Okay, so here we will place our SAD aperture. So this is the related to the instrumentation. So the answer will be the back focal plane of your objective lens. Okay, so here our next question will be moving towards the scattering angle of electron. So there are a different kind of a diffraction. Electron also diffract, and there you have seen the XRD, okay, which is a X-ray diffraction. So the scattering angle of electron diffraction in compared to X-ray diffraction is smaller, bigger, or almost same, or depends on the material. So can you answer this question, or have you seen, or if you have done your or if you have any experience related to the XRD and the electron diffraction, then can you comment on the scattering angle of both, or the relation between both? Okay. Okay, so this will be the slide related to that. So the electron diffraction pattern. So basically, you just go through this slide, and I will also show you that in the slide. Okay, so since it is also saying that that depends on the material. Okay, so material is also one factor, but here that is not a major factor, because it is altogether a different phenomena if you will take any specimen with the crystalline or the polycrystalline or the amorphous. Okay, so here when you will see, so it is asking about the angle. Okay, so here when the incident beam will come, and this will be the direct beam and this will be the diffracted beam. Okay, so in the electron diffraction you can see this is diffracted. Okay, so here the angle 2 theta will be this in the electron diffraction, right? But in XRD, can anybody guess the XRD? The there is one law which is very famous in when we understand the XRD. So can you tell me the name of that law? Yeah. Yes, exactly. So if you remember, which I will also show you in the further slide. So if you remember, so this is the Bragg's law. Okay, Bragg's law is relationship of the n lambda equals to 2d sine theta. Okay, d is this, the interatomic layer, distance between this layer. Okay, so here the this will be come at an angle theta, and this will be so 2 theta will be here. Okay, this will be 1 theta, this will be 1 theta, incident angle and the reflection angle. So here if you will see, this will be the diffraction in electron diffraction, you can say, or the scattering angle here will be like this. But here the scattering angle, here the electron is coming and it is reflected in this direction. Okay, so can you guess that, so here it will be 180, it will be theta, it will be theta, so it will be 2 theta. So what will be this angle between the incident angle and the reflection angle? Okay, so this will be somewhere 180 minus 2 theta. Okay, but here this angle is smaller when you will consider the electron diffraction, but here it is altogether going in a different direction. Okay, so by just seeing this, or by just if you will know, or if you remember the diagram of your Bragg's law, then it is just a guess. Okay, so here there will be a must thing which you will see in your in the upcoming lectures, that there will be the interference or the constructive interference or the destructive interference, how this relation will come, and lambda equals to 2d has 2d sine theta, where the lambda is the wavelength, and this is d is the distance between this interatomic, and the theta is the angle. Okay, so here the angle is here which is higher as compared to the electron diffraction. So the scattering angle in the electron diffraction will be smaller as compared to the XRD, or you can say the X-ray diffraction. Hmm. Okay, so you are saying in the electron micros or there we the focus will be the more, right? Okay. Okay, fine. Okay, so this I was not aware, but thank you for this opinion also. That's why I was always welcoming for the this kind of interaction. So yeah, I will also read, and probably this has some logic, okay, because the focus is also important when any kind of a incident beam is coming, so that will also give some relation between the scattering angle, so which is also right. So yeah, thank you for that. So here the angle between the direct and the diffract beam increase. So this I have just shown you the one slide where I have just shown you the some angle, okay, between the direct beam and the diffracted beam. So so at least this you can guess that what could be the relation between the interatomic distance and the wavelength. Decreasing interatomic distance and decreasing wavelength. Okay, let's see. So here I have, as I have shown you the Bragg's equation. So the angle between the direct and the diffracted beam increases. So it is asking about the, okay. So here again the question is related to the angle. So here in this equation the relation is, so suppose if you will keep the n constant, suppose we are solving this equation for n equals to 1, let's say, okay. So if the angle between this will increase, okay, so how the angle should be increased? So if we will, what could be the relation? So decrease the interatomic distance, okay, decrease the interatomic distance. So if suppose decrease means when we will decrease the d. So suppose if we will take the theta which is small, or if we will take it as a theta, because if theta will be the smaller, then sine theta will be the theta. So when we will decrease the interatomic distance, there will be the increase in the angle. Why? You just guess, because when you will d equals to what will be there, n lambda upon sine theta. So you just have to solve the relation between here theta and the d. Are you getting it? Yes. Okay. So here the n lambda equals to 2d sine theta. So here it is. So first thing is your angle. So angle is what? Sine theta. So sine theta, it means to say n lambda upon 2d. So theta and the d will come into the inversely proportional. Okay. So when you will decrease the d, the theta will increase, right? And the sine theta is directly proportional to the lambda, because n lambda equals to 2d sine theta. Okay, did you get it? Here the d is inversely proportional to the theta and the lambda is the directly proportional to the theta. So here we wanted to increase the theta. So for that we have to decrease the interatomic distance, which is nothing but the d, and we have to increase the wavelength, which is nothing but the lambda. So from the, this is very simple. So you can say that by decreasing the interatomic distance and by increasing the wavelength, we can increase the angle between the incident beam and the reflected beam. I hope you got it. Okay. So, okay. So this is again why people are joining so late. Okay. So what is the zone axis of 100 and 010 zonal planes? Okay, so if you have seen the lectures, there is one lecture where you have to there is a relationship. Okay, so which I will show you in the further slide. This could be the vice versa also, that they can give you the zonal planes, you have to find out the zonal sorry, they can give you the zonal axis, you can find out the zonal planes. Okay, so here is the relationship. So zone equals to what? Zonal planes plus zonal axis. So there will be so there will only be strong diffraction from planes of atoms which are nearly parallel to the incident electron beam. So it is related to some this axis and the planes because every crystal has their orientation. So the planes and axis is very important. So if you will go through this lecture, you will be able to get some clear idea. But here, as per the question, I just wanted to give you the formula. So here you can see we wanted to find out the zone axis, which is nothing but the UVW. So UVW is related to the zonal plane. How? So zonal plane is HKL. So this is the formula, like if you want to find out the U K1L2 minus K2L1. For the V, L1H2 minus L2H1. For W, H1K2 minus H2K1. So can anybody quickly give me or solve the UV, or at least some any of one component of the zonal axis, or you can guess that what could be. This is just a simple mathematics. This is formula for 0 and 010, or if you can solve or something. This will be, if this will be your journal. I hope this kind of question is there in your assignment or not. It is. Okay, so it is there now, this kind of a question. Okay, so fine. I hope this will be able to help to solve. So just remember this formula, and you guys will be able to solve this question. So I did not attempt this question. So I am giving this to you because formula is there, everything is there, the value of HKL is there. You have to just find out the UVW, and you can get your zonal axis. Okay, so the relationship between the real lattice and diffraction pattern of a particular specimen can be expressed as what? So this is also a formula based question. R into D equals to constant, R by D equals to constant, root over R by D is constant, none of the above. Guess? Guess? There are, I think the strength is little less today. Only 15, 14, 15 has joined. So it's fine. Okay. So here, when you will go through this slide, this is I think the last slide, and mostly this will be covered in your week 5th, but they have given you. So this is also based on your optics. So the relationship between the real lattice and the diffraction pattern. Okay. So in order to understand the geometry of electron diffraction, we can ignore the lens system, which merely magnifies the diffraction pattern, and consider the much simpler ray diagram. Okay, so this is a very simpler ray diagram. As you can see, there will be the object, and there will be the lens, and the ray is coming, and this will be the focus, and here you will get the inverted image, and after this there you will get a magnified image. Okay, so here it is also you are keeping the n equals to 1 and lambda equals to 2d sine theta. Since the theta is very small, so you can take sine theta equals to theta, so the lambda will be d into 2 theta. So 2 theta equals to lambda by d. Okay, so here the distance R is what? The distance of diffracted spot from direct beam. Okay, so the distance from where the diffracted spot, it means from where the incident beam is coming, and from where it will give the diffracted spot, okay, of the direct beam. So which is nothing but the R, and it is inversely proportional to the D. Okay, so D spacing of the diffracted planes. So here, if there will be incident beam will be coming, and this will be your undiffracted beam. Okay, and this will be your diffracted beam. So from here, if you will get the relation R by L, so here this will be your tan 2 theta. This will be R and this will be your L. So R by L equals to tan 2 theta. So here also, if the theta will be the smaller, tan 2 theta equals to 2 theta. So 2 theta will coming nothing but will come as a R by L. So when you will derive this equation, 2 theta equals to R by L. So R by L equals to, here 2 theta is also, from here you will get the lambda by D. So lambda by D equals to R by L. So by the cross multiply, R sorry, L lambda equals to RD. So from here you will get the relation. So which is what? R, it is asking about the R and D equals to what? So R by D, R into D, root over R by D. So from here, R into D equals to L lambda. So L lambda is what? L is also constant. This is the distance, and the lambda is wavelength, which is also constant. Depends on the incident of your incident beam wavelength. So this is also constant. Or you can also, here it is saying the camera constant. The name of this L lambda is camera constant. So the R into D will be constant. From this relation you will get this. So answer will be the R into D equals to constant. So this I have just shown you the slides where you can also get the answer of this kind of a question. Camera length in TEMR. So independent of the specimen and not constant for the instrument, dependent of the specimen and constant for the instrument, independent of the specimen and constant for the instrument, dependent of the specimen and not constant. So this is a factual question. So this is asking about the camera length. So here you can see here, this is as the camera length and the electron wavelength are independent of the specimen and are constant for the instrument. Okay, so this is a factual kind of a question that you have to remember, that it is independent. If you will get any kind of a specimen or different specimen, then also the camera length and the electron wavelength are it independent from whatever specimen you are using, and which will be the constant for the instrument. So again, the same thing. Okay, so here in TEM, the diffraction contrast provides information about what? So this is very interesting question if you know the contrast generation in TM. So can you give me the answer and why? Okay, fine. It is right answer. So can you please also tell me that why the orientation affects the or it is giving me the contrast, or what is happening there, or you can give your any logic or whatever you have gone through the lecture, or anybody else or also wanted to guess or answer, they can also do the same. Okay, I will just show you the slide then. Huh? Yeah, please say. Orientation, why orientation? You can see the slides, and also you can say I have just opened the slide also. Hmm. Hmm. Okay, fine. Okay. Okay, right. So suppose for an example, you have any specimen. Okay. You got any specimen and it is a single phase. Okay. You don't have the alloy kind of a thing. So you only have the difference in the crystal. Crystal orientation is different because it is a your I mean not a alloy. It is a single material. Okay, or you can say a single phase material. So if a crystal is orientation, so oriented close to zonal axis, many electrons are strongly scattered to contribute to reflection in the diffraction pattern. Okay, so here suppose if this is appearing as a darker and the other side is appearing as a brighter. Okay, so here it is also somewhere related to the scattering of the electron. Okay, or the passing of the electron. So only a few electrons pass in such area without any interaction and therefore dark contrast appears. This is dark, so the few electron pass from here, the few electron, so when the incident electron beam will come, the scattering will be more due to the crystal orientation, right? So it is because of the crystal orientation also. Suppose the 100% incident electron beam is coming and only the few electrons can pass, so that area will appear as a darker, okay, in bright field image. So that will also generate due to the crystal orientation, due to the difference in the orientation of the crystal, the scattering or the passes of the electron will be the different due to the orientation also. So that will also lead to give you the different or the contrast generation in TEM. Okay, so this will be also due to that. So here the diffraction contrast, it is saying, provides information on the orientation of the crystal in a polycrystalline sample, right? It is not a single crystalline sample if you will take, but it is a not a multi-phase. Here you will not see a then it will give you some other contrast also. If you have a single phase material but it is a polycrystalline material, not a single crystalline material, then also due to the difference in the orientation of the crystal. Why? Because due to the difference in the orientation of the crystal, the passes of the electron will differ. Okay, so the here from the crystal which is appearing darker, from there the passes of the electron which is less as compared to the brighter side. Here the electron will pass in a more quantity, but here the electron passes will be lower as compared to the other places, and that place will appear as a darker. So this will lead to generate a contrast due to the and it which is nothing but the diffraction contrast, and which is related to the orientation of the crystal. So this will be the answer. Okay, so what will be the contrast generation? This is also the same question due to the atomic number effect again, but this is in the TEM, and this is high angular, this dark field image of an alloy containing aluminum and the copper. So this is also alloy. So can you guess that this is also the same kind of a question, but this is related to the atomic number effect. So but this is in the TM hat imaging. So do you have any idea about this or any relation if I will show you this? This is the high angle scattering. Okay, so here what is happening? It is in this half mode. The probability of scattering events rises for heavier atom. Okay, so atoms with high number of protons, it means the higher the atomic number, offers the possibility of, so this will be giving you the offers the possibility of obtaining chemical contrast. So the aluminum will be having a lower atomic number and the copper will be having a higher atomic number. So can you now tell me that what could be the answer of this question, that contrast generation due to the atomic number effect here? So from this slide, if you can guess that which will appear a brighter and which will appear a darker, aluminum or the copper? So here the element which is having a higher atomic number, right, that will scatter strongly and that will appear brighter. So here which is higher atomic number? The copper is higher atomic number. Okay, so that will scatter more and that will appear as a brighter. But due to the lower atomic number of the aluminum, the scattering will be the less and this will appear as a darker. Okay, so here the copper will be brighter and the aluminum will be darker because of the difference in the atomic number effect. But just be aware that one question also I have taken previously, there will be no any high angle scattering. This is the high angle scattering mode. Okay, so this also you need to be considered that why this is happening. This is very basic and simple question. Which of the following information can be obtained from a TEM? So I hope, again, if I will show you this diagram, maybe you will be able to answer. So what is the need of TEM? Can anybody tell me that why we have optical, we have this SEM, we have other things, so many things, that why we need TEM, why we went for, or suppose if you're doing some project and you require a TEM, why you require a TEM, what is the need? Just a basic question. Okay. Hmm. Right, right. So, which is right, correct. So, the preparation of the sample in TM is very difficult. Why? Because here the electron beam is transmitting. So, the sample should be very, very, very thin. Okay, such that the electron can transmit. So here you can see, as he has said, that we can see the dislocations, we can see the atoms, we can see the crystal orientation also. So from TM you can get the higher resolution in a atomic level also. Okay, so that's why we go for the TEM, for the better resolution or for the better specification of any specimen. Okay, we wanted to see some more thing, or what is the exactly phenomena is happening in the specimen. That's why we went for the TM. So this will be give you also, because it is TM, so morphology also you can get. It is also kind of a this morphological, you can get the some surface morphology or the internal, you can get the crystal structure and orientation, just I have mentioned, and the compositional details, and this is how you will get that, you will get to know in your further lectures, that how you can get from the TM. So the answer will be the all of the above, and this is the basic I mean the schematic, that how I have also shown you. So there will be also the X-ray detector will be there, and there are so many things which is incorporated in your TEM instrumentation, and there is some bright field and ADF dark field and high angle scattering detector. So there are many things you can get many observations from this TM. So I think for this week I have prepared this kind of a question, and I hope this kind of a questions are there in your assignments also, which will at least, I hope that at least you will be able to solve more than the 50% by seeing this kind of a questions. So, and this will make your assignment much easier. Yeah, yeah. So I hope the main reason behind this doubt clearing is that that you guys are able to solve your assignments, you know, in a more efficient manner. And if you will have any doubt, that's why I'm preparing this kind of a question, because I also have to go through the slides and have to see the lectures. Okay, because this is covered throughout the week. Okay, it is not just a one lecture or the any one portion. So I hope that this will be helpful for your assignment solution. Okay, so here I'm stop presenting my slides, and it is 8.8, and so if you have any questions of the today's questions or you wanted to discuss something else, then feel free to ask. Yeah, exam pattern I have asked, but they have said that that will, I mean, it could be anything. So be ready for both. I mean, but most probably it will be online kind of a thing. So it is not like you have to, means like, write in the paper and you have to scan and submit. So most probably this will be mm, online, but at least you will be able to write some answers and the questions also. So, because they have also not said anything, which is very uh, robust that, okay, this will be your exam pattern. Yeah. Anything else? Yeah, yeah, sure, sure. If somebody is having question, I am here. And if not, then you may leave. Yeah, sure. Please ask. In TM? No, 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 no. You can use thin samples that because why so only thing is why, because there is some when you go for the TM, there is some sample preparation is required. For SEM you can take any samples, from for optical you can take any specimen, but for the TM the sample preparation is very very important. Why? Because they will, if you have ever gone for the TM analysis, then they will give you a copper grid. Okay, so you have to put your sample there. Okay, so for that, you have your electron beam should transmit from your sample or through your samples, then only you will be able to get the image. So if your sample will be the thick, your electron cannot pass through your samples. So that's why the thinness of sample is very very important. Yeah, sure, welcome. Anybody else wanted to have ask or have some question? If not, then thank you for joining.